The cosmos will not last forever. We are going to explore 15 ways the universe could end, according to the most advanced ideas in modern physics. By the end of this journey, you will understand the fundamental forces that might one day write the final chapter of everything. We will investigate how space itself could be torn apart and why all matter might simply fade away. What do you believe is the most haunting possibility for our ultimate end? A cup of coffee never warms the room. It is the room that eventually cools the coffee. Our universe appears to be on a similar one-way journey. The Big Freeze, often called the heat death, is the most widely accepted forecast for our cosmic future, a conclusion drawn from the fundamental laws of thermodynamics. These laws tell us that heat always flows from hot objects to cold ones, and that systems naturally progress from order to disorder. In an ever-expanding universe, driven by the mysterious force of dark energy, this process plays out on the grandest possible stage. Galaxies will race away from one another, their light stretching into invisibility. Every star in every galaxy will ultimately burn out, plunging the cosmos into darkness. Even the mightiest black holes are not eternal. They slowly leak radiation until they too vanish in a final whisper. What remains is a universe that is unimaginably cold, perfectly uniform, and utterly still. This state of maximum entropy, where energy is spread so thin it becomes useless, is the ultimate equilibrium. It is a silence so complete that no new sound can ever be made, no new star can ever be born. This is the end of time's arrow, a future where nothing happens, and it keeps on not happening forever. Yet this quiet fading is just one possibility. What if the universe does not fade away, but is instead torn apart from the inside? Our universe could one day reverse its great expansion. This is the Big Crunch, a cosmic collapse where every galaxy, star, and atom falls back together. Imagine the force of dark energy which now pushes the universe apart, somehow weakening and losing its dominance. The relentless pull of gravity would then take over, reeling everything back in. We would not see it coming for billions of years, but the end would be swift and violent. Distant galaxies would begin to blue shift as they rush toward us, the night sky growing brighter and hotter. The cosmic background radiation, the faded glow of the Big Bang, would heat up from its frigid state to a searing blaze. Galaxies would smash together in chaotic mergers, and supermassive black holes would devour one another, growing into monstrous singularities. Space and time themselves would warp beyond recognition, the very fabric of the cosmos tightening like a clenched fist. Everything that ever was, every planet, every life form, every memory, would be compressed into an infinitesimal point of infinite density, a singularity from which nothing could escape. This final state mirrors the universe's birth, but in reverse. Some theories suggest this singularity might not be a true end. It could be a rebirth, a moment of such immense pressure and energy that it triggers a new Big Bang, spawning a fresh universe from the ashes of the old. This idea of a cyclic cosmos breathing in and out for eternity is profoundly compelling. But could anything carry over from one cycle to the next? Would the laws of physics reset, or could some faint imprint of our universe persist? The collapse would likely erase time itself along with all information, making each new cycle a complete and total blank slate. This concept forces us to confront a chilling possibility. What if the end is not a quiet fade or a dramatic collapse, but a violent and instantaneous shredding of reality itself? That silent, cold end is not the only alternative to a fiery collapse. There exists a third, far more violent possibility, a fate where the universe does not fade or crunch, but is actively ripped to pieces. the very fabric of space-time could tear apart, shredding galaxies, stars, and even the atoms that make up our bodies. This is the Big Rip, and its trigger is a particularly vicious form of the very force driving our expansion today, dark energy, but not just any dark energy. This scenario requires something called phantom energy, a hypothetical substance with such intense negative pressure that it causes the expansion of the universe to accelerate at a runaway rate. The key to this terrifying idea is a number known as the equation of state parameter. For phantom energy, this value is less than -1. Think of it like this. If the universe's expansion were a car, our current understanding of dark energy is like gently pressing the accelerator. Phantom energy would be like welding the pedal to the floor, with the engine screaming and the speedometer needles spinning uncontrollably until the entire vehicle flies apart. Theoretical physicist Robert Caldwell, who helped pioneer this idea, calculated that if phantom energy is real, the universe has a finite and calculable lifespan before it literally comes undone. The Hubble constant, which measures the current rate of cosmic expansion, would not just increase, it would skyrocket to infinity. The disintegration would begin on the largest scales. First, the gravitational glue holding galaxy clusters together would be overwhelmed. Galaxies would be flung into the growing void, isolated from one another forever. Then the force would target individual galaxies. Stars would be torn from their orbital paths, sent adrift in a rapidly emptying space. As the end drew near, the phantom energy would attack solar systems. Planets would be ripped away from their suns. Then it would come for the planets themselves and the stars, tearing them apart against their own gravity. In the final, fleeting moments, the bonds holding atoms together would be shattered. Atomic nuclei would be torn from their electrons. Even the protons and neutrons themselves would be ripped apart, their constituent quarks scattered into a universe that has become a collection of disconnected particles, unable to ever interact again. Caldwell famously described this end by saying, "The universe ends not with a whimper but a rip. It is a lonely, absolute disintegration." What would it be like to witness those final seconds, to feel the planet literally come apart beneath your feet? This ultimate dissolution forces us to question the true nature of the dark energy that surrounds us. But what if the end is not a single, dramatic event, but a slow, imperceptible decay from within? That silent, imperceptible decay from within is perhaps the most unsettling end of all. Our entire reality could be built on a foundation that is fundamentally unstable. Think of our universe not as resting at the bottom of a deep well, but as sitting in a shallow dip on the side of a much steeper slope. This is a metastable state, a precarious balance that could be shattered at any moment by a random quantum event. A single, tiny fluctuation could be enough to push the entire system over the edge, initiating a process known as vacuum decay. The culprit here is the Higgs field, an invisible energy field that permeates all of space and is responsible for giving particles their mass. What if this field is not in its true, lowest energy state? A bubble of this true vacuum could spontaneously form, like a blister in the fabric of space-time. The laws of physics inside this bubble would be completely different. Fundamental constants like the speed of light or the strength of gravity could be rewritten. This bubble would then expand in all directions at nearly the speed of light, and there would be no warning. One moment you exist, the next, an impenetrable wall of new physics is upon you, instantly transforming everything in its path. Atoms would simply cease to hold together. The very forces that bind matter would be erased, leaving behind a universe that is utterly alien and completely hostile to any structure we recognize. The physicist Stephen Hawking highlighted this as the ultimate existential risk. a phase transition that could erase the cosmos as we know it. The probability of this happening is incredibly low, but it is not zero. The critical factors are the height of the energy barrier holding our universe in its current state, and the quantum tunneling rate that could allow it to jump that barrier. How would such an event propagate? It would be a wave of pure change sweeping through the galaxy and beyond, leaving nothing recognizable in its wake. There is no way to outrun it, and likely no way to detect its approach until it is far too late. This invisible threat, born from the quantum realm, forces us to question the very ground of our being. But what if the end is not a sudden rewriting of the rules, but a slow, inevitable erosion of matter itself? This slow erosion of matter is not just a possibility, but a prediction woven into our most ambitious theories of physics. The very protons at the heart of every atom you have ever touched may not be permanent. They could possess a secret, unimaginably long timer, ticking down toward their own spontaneous disintegration. This is proton decay, a concept that emerges from grand unified theories. These theories aim to accomplish what Einstein dreamed of, merging three of the universe's fundamental forces: the electromagnetic force, the weak nuclear force, and the strong nuclear force, into a single, elegant framework. In such a unified picture, a proton, long thought to be stable, could actually fall apart. The process would likely involve a hypothetical particle called the X boson, a messenger of this grand unification. The half-life of a proton under this model is staggering, estimated to be at least 10 to the 34 years, a number so vast it dwarfs the current age of our universe. But given an eternity, even such an infinitesimal chance becomes a certainty. One by one, the protons in every atomic nucleus would decay. A typical decay might see a proton transform into a positron, the antimatter counterpart of an electron, and a neutral pion, which would then itself decay into high-energy photons or light. The implications are absolute. All complex matter would be dismantled from the inside out. Imagine a distant future where every planet, every star, and every speck of interstellar dust simply dissolves. The mountains would fade, the oceans would vanish, not by being worn away, but because the very atoms that constituted them would have spontaneously turned into a faint, diffuse glow of radiation and lightweight particles like electrons and neutrinos. What happens to the most resilient structures in such a universe? Even black holes, which feed on matter, would eventually find their food source disappearing. As they absorb the products of this universal decay, their own long-term fate becomes the next great question. The physicist Andrei Sakharov once explored how such asymmetric decays could have shaped the early universe, creating the matter-antimatter imbalance we see today. Now, that same process would act as the universe's ultimate cleanup crew, erasing all tangible structure. Experiments deep underground, like the Super Kamiok and detector in Japan, have spent decades watching vast tanks of pure water, searching for the telltale flash of light that would signal a single proton's death. So far, they have found nothing, proving that the proton's lifetime is at least astronomically long. Yet the profound possibility remains that our reality is built on a foundation that is only temporary. If all matter is destined to fade into a thin, radiant mist, what ultimate destiny awaits the last great giants of the cosmos, the black holes themselves? Those black holes, the last titans of a faded cosmos, are not eternal prisons. They too face a slow but certain dissolution, a process that reveals a deep and mysterious connection between the very large and the very small. This is black hole evaporation, a concept pioneered by Stephen Hawking that forever changed our understanding of these gravitational monsters. Hawking realized that the vacuum of space near an event horizon is not truly empty. Due to quantum fluctuations, pairs of virtual particles, one of matter and one of antimatter, constantly pop into and out of existence. Normally, they annihilate each other almost instantly. But at the very edge of a black hole, a dramatic theft can occur. One particle falls across the event horizon while its partner escapes into space. To an outside observer, it appears the black hole has just emitted a particle. The energy for this creation comes from the black hole's own gravitational field, causing it to lose a tiny, almost immeasurable amount of mass. This is Hawking radiation. Hawking famously declared that because of this, black holes are not so black after all. They glow with a faint thermal heat. The temperature of this radiation is inversely related to the black hole's size. A massive black hole, like the one at the center of our galaxy, is incredibly cold, emitting far less heat than the cosmic background radiation that bathes it. It is actually absorbing more energy than it emits, but as the universe expands and cools, a tipping point will come. The black hole will begin to lose mass in earnest. This evaporation is a slow process at first. A black hole with the mass of our Sun would take 10 to the 67 years, a number with 67 zeros, to evaporate. That is an almost inconceivable timescale. Yet, for much smaller primordial black holes, hypothetical remnants from the universe's first moments, the process could be happening much faster, and their explosive ends might even be detectable. As a black hole shrinks, its temperature rises. The smaller it gets, the hotter it glows, and the faster it loses mass. In its final moments, this slow leak becomes a torrent. A black hole that has lived for eons would shed its remaining mass in a sudden, brilliant flash of high-energy radiation and particles, a final shout before it winks out of existence entirely. This breathtaking idea, however, comes with a profound puzzle: the black hole information paradox. According to quantum mechanics, information about what falls into a black hole, the specific arrangement of particles that made up a star, a planet, or a person, can never be truly destroyed. But if the black hole evaporates into a random, featureless spray of heat, where did that information go? Its complete disappearance would violate a fundamental law of physics, suggesting our understanding of reality is deeply flawed. The resolution to this paradox remains one of the greatest unsolved problems in theoretical physics. It forces us to ask, when the last black hole vanishes in a puff of radiation, what ultimate secrets does it take with it? This slow fading of the last structures hints at another, even more radical possibility. What if the universe itself is not a unique event, but just one bubble in an infinite, bubbling foam of realities? That unstoppable wall of transformation has a close and equally terrifying cousin. The Big Slurp is a specific and violent version of vacuum decay, one that does not wait for a random quantum fluctuation. Instead, it could be kicked off by a deliberate or accidental event of immense energy. Imagine a single, catastrophic particle collision, perhaps within a future particle accelerator of unimaginable power, or a rare cosmic cataclysm like a magnetar flare, providing just enough concentrated force to punch through the energy barrier holding our universe in its fragile state. This event would nucleate a bubble of true vacuum, a region where the laws of physics are fundamentally different. The bubble's wall would then surge outward at the speed of light, a spherical front of pure change. There is no force in our universe that could stop it, and no warning we could possibly receive. The moment the bubble forms, its own light-speed expansion is the first and only signal of its existence. Physicist Lisa Randall has explored how such a transition could be a genuine, though highly speculative, risk in certain theoretical frameworks, particularly those involving extra dimensions. The landscape of string theory suggests our cosmos is just one of a vast multiverse of possible vacuum states, each with its own unique physical laws. Our universe might simply be sitting in a comfortable but temporary valley, while a much deeper, more stable valley lies just over a neighboring energy hill. The big slurp is the moment we tumble into that deeper valley. As the bubble wall passes through a galaxy, it would not destroy matter in an explosive sense. It would do something far more absolute. It would rewrite the very rules of existence, the strength of the nuclear forces, the mass of an electron, the very existence of atoms as stable structures. All of it could be instantly and irrevocably altered. One moment, a star system thrives. The next, it is a soup of unrecognizable particles governed by alien laws, a place where life and light as we know them are impossible. This raises a haunting question. Could our own thirst for knowledge ever become our undoing? Could a high-energy experiment designed to uncover the deepest secrets of reality inadvertently become the trigger that ends it? The energy required is almost certainly beyond any technology we can foresee, and the natural probability is vanishingly small, but the theoretical possibility forces a profound ethical consideration. It connects the fate of our entire cosmos to the endeavors of a single, curious species on a pale blue dot. The idea of a sudden, physics-altering end is perhaps the most absolute, for it erases not just matter, but the very stage upon which reality plays out. Yet this focus on a single, catastrophic transition leads us to a different kind of end, one not of sudden change but of slow, cosmic disassembly, where the very building blocks of space and time begin to unravel. The black hole era is the final, fading heartbeat of an active cosmos. Long after the last star has died, these gravitational giants will dominate the universe for trillions upon trillions of years. We are living in the stelliferous era, a brief, bright age filled with shining stars, but that will give way to the degenerate era, a far longer period populated by the cold, dark cinders of dead stars, white dwarfs and neutron stars slowly cooling over eons. And then the black hole era begins. In this unimaginable stretch of time, black holes will be the last large structures in existence, the sole rulers of a profoundly dark and empty space. They will not be silent rulers, however. Through Hawking radiation, they will slowly, inexorably leak their mass away. Picture a supermassive black hole with the mass of millions of suns, glowing with a temperature barely above absolute zero. Its evaporation is a whisper, a process so slow it makes the current age of the universe feel like a single blink. Physicists like Freeman Dyson have pondered whether any form of consciousness could survive in such an era, subsisting on the unimaginably tiny trickle of energy from these dying titans. The timeline is almost beyond human comprehension. While smaller black holes will vanish first, the supermassive ones at the centers of former galaxies will persist the longest, their lives measured in googolls of years, a one followed by 100 zeros. As they evaporate, they release a faint drizzle of particles and energy into the void. The universe grows colder and colder, its temperature plummeting toward an absolute zero that it may never quite reach. The significance of this era is its sheer duration. For the vast majority of the universe's future timeline, this slow evaporation of black holes will be the only significant game in town, the last active process in a cosmos sliding toward equilibrium. And then, one by one, they too are gone. The very last black hole in existence will, after an eon of solitude, suddenly heat up. In its final second, it will release a burst of light and particles, a final, brilliant message to an audience of none. After that flash fades, what remains? Only a thin, cold soup of isolated particles, photons and leptons like electrons and neutrinos, all drifting endlessly apart in an ever-expanding, nearly perfect void. Could any information, any record of all that once was, survive in this sea of ultra-low-energy radiation? It seems all structure, all history would be lost to the ultimate silence. This staggering decay forces us to ask if time itself has any meaning when nothing ever changes again. Yet this slow fade is not the only possible finale. What if the end is not a gradual dimming, but a sudden, violent collision between our universe and another? Our universe could reach a point where the very concept of time loses all meaning. This is not merely a slowing down, but a complete cessation of temporal flow, a final, frozen state known as the end of time. As dark energy accelerates the cosmic expansion, the universe becomes a profoundly lonely and empty place. Galaxies vanish over the cosmological event horizon, the boundary beyond which no light or information can ever reach us. Eventually, every star and black hole evaporates, leaving behind only a thin, cold sea of radiation drifting endlessly apart. In this distant de Sitter universe, a remarkable threshold is crossed. There are no longer any processes left to measure change, no stars burning, no particles decaying, no clocks ticking. Without change, can time truly be said to exist? The physicist Julian Barber argues that time is not a fundamental entity, but an emergent illusion born from sequences of change. If all change stops, the illusion shatters. The cosmos would become a single, static, and eternal configuration, a frozen snapshot of a single moment. There is no past to remember and no future to anticipate. There is only a perpetual and undifferentiated now. This challenges our deepest intuitions. How could consciousness or information persist without a temporal flow to anchor it? A thought itself is a process, a sequence of neural events. In a timeless universe, even the flicker of a single idea would be impossible, frozen in an instant that never progresses. This philosophical endpoint suggests that our experience of reality is inextricably linked to the arrow of time, an arrow that may one day simply stop flying. This profound stillness, however, leads us to a more dynamic and ancient idea. Could the universe avoid this frozen fate by being part of an endless, repeating cycle? This cosmic breath, an endless cycle of collapse and rebirth, offers a dramatic alternative to a final, silent end. The Big Bounce transforms the universe from a single, linear story into an eternal epic, with our own Big Bang merely the latest chapter in an infinite series. This idea is central to cyclic universe models, and it finds a compelling foundation in the mathematics of loop quantum cosmology. Here, the crushing gravitational collapse that would lead to a singularity in classical physics is halted by a powerful quantum repulsion. When the universe contracts to a state of incredible density, the fabric of spacetime itself resists, pushing back against total collapse. Instead of a dead-end singularity, the universe reaches a minimum size and then bounces, exploding outward in a new period of expansion, a new Big Bang. This elegant mechanism solves a profound puzzle of the standard Big Bang model, the initial singularity problem, by simply removing the need for a true beginning from nothing. Our universe may not have been born from a void, but from the death of a previous cosmos. The work of physicists like Neil Turok and Paul Steinhardt further explores how such cycles could be driven by the dynamics of fields moving through higher dimensional spaces, a concept from string theory known as Brane cosmology. In this vision, our entire three-dimensional universe could be a membrane or brane colliding with another in a recurring, universe-spawning event. Each cycle would reset the cosmic clock, but what if anything is carried over? Does any information, any faint echo of the previous universe, survive the violent transition? Some theories suggest that the specific arrangement of the cosmic microwave background, the oldest light in our sky, could contain subtle imprints or scars from the universe that came before ours. Imagine the cosmos as a phoenix perpetually rising from its own ashes. Yet, each new universe might not be an identical copy. The fundamental constants, like the strength of gravity or the mass of the electron, could be randomly reshuffled with each new bounce. In one cycle, the forces might be perfectly tuned for stars and planets and life to form. In the next, the constants could be different, resulting in a sterile, fast-expanding void or a universe that collapses again almost instantly. This introduces a breathtaking possibility. Our universe seems finely tuned for complexity, but perhaps that is not a miraculous coincidence. In an infinite series of cosmic cycles, it was statistically inevitable that at least one universe would have the right conditions for us to exist within it and wonder at its origins. Could life or some form of consciousness re-emerge in each new universe where the constants allow? The Big Bounce offers a vision of immortality for the cosmos itself, but it raises a profound question about our own place in this grand cycle. Are we merely a fleeting pattern in one iteration of an infinite sequence, or could some deeper structure connect all these realities across the eons? This concept of a cyclic multiverse, with its diverse potential endings and beginnings, forces us to reconsider the very nature of eternity. Our cosmic bubble may not be expanding forever. According to the theory of eternal inflation, the vast multiverse undergoes endless expansion, but within it, pocket universes like our own form when this inflationary drive stops in a localized region. We exist within one such stable bubble, but its stability is not guaranteed. A single quantum fluctuation or an interaction with the boundary of a neighboring bubble universe could cause our local patch of spacetime to collapse. This would not end the entire multiverse, just our observable part of it. The framework for this comes from the string theory landscape, a dizzying array of possible vacuum states, each with its own physical laws and levels of stability. Our universe occupies one relatively stable valley in this landscape, but a more stable one might lie nearby. The physicist Alan Guth, who pioneered the inflationary concept, has detailed how such a transition is a matter of probability, governed by quantum tunneling. The mechanism likely involves the same type of scalar field that drove inflation in the first place, suddenly rolling down its energy landscape to a new, lower minimum. This event would not be a gentle descent. It could trigger a violent contraction, a local big crunch that pulls our entire galaxy cluster inward, or it could initiate a vacuum decay, rewriting our local laws of physics in an instant. The key factors are the rate of this quantum tunneling and the intricate geometry of the multiverse itself. While countless other bubbles continue to expand and spawn new realities, our own cosmic home could be silently deflating. What would we see from inside a collapsing bubble? Distant galaxies might appear to slow their recession, then begin rushing toward us in a growing blue shift, the first hint of a local gravitational reversal that the wider multiverse would never notice. This perspective is both humbling and unsettling, suggesting that our universe's ultimate fate could be a purely local affair, a single flame guttering out in an infinite, eternal fire. Our cosmic stability might be a carefully maintained illusion, a temporary equilibrium that is slowly being eroded. This is the false vacuum collapse, a scenario where our universe's fundamental state is not its final resting place but a precarious ledge. The Higgs field, which gives particles mass, might currently be trapped in a false vacuum, a state of relative stability that is not the absolute lowest energy configuration possible. Unlike a spontaneous quantum fluctuation, this collapse could be triggered by a gradual accumulation of tiny shifts. over cosmic timescales, the field could slowly evolve or be nudged by influences from other realms in the multiverse until it finally tips over the edge. The work of Nobel laureate Steven Weinberg on the cosmological constant touches upon these profound issues of vacuum stability. Some calculations within the standard model of particle physics suggest our electroweak vacuum might indeed be metastable. If certain parameters, like the mass of the top quark, are just right, then our entire universe is living on borrowed time. The trigger for the end may have been set at the Big Bang, a slow-burning fuse that is only now reaching its end. How close are we to that final, inevitable tipping point? The collapse would manifest as a wall of true vacuum, a phase transition front expanding at the speed of light. For this bubble to grow and consume the universe, it must reach a critical size, overcoming the energy cost of creating its new reality. In the hot, dense early universe, high temperatures actually helped stabilize our false vacuum, making such a collapse less likely. But as the cosmos expanded and cooled, that protection faded, leaving us in a more vulnerable state. Imagine the universe itself as a dam holding back an ocean of a different reality. For eons, the structure has held, but cracks are slowly forming from the relentless pressure of quantum tides. One day, a single crack will reach a critical length, and the entire dam will shatter in an instant. The wall of true vacuum would not be something you could see coming. It would simply arrive, rewriting the laws of physics in its wake. Atoms, forces, and the very concept of matter as we know it would cease to have meaning. This delayed but inevitable doom forces a profound question. Could a sufficiently advanced civilization, understanding these parameters, ever find a way to prevent the collapse or even steer the universe into a more stable state? The fate of everything might one day depend not on chance but on cosmic intelligence. This possibility of a triggered end connects to an even more ancient and elemental force, one that has shaped the universe since its first moments. There is another profoundly optimistic vision for the final state of everything. The universe could awaken in its dying moments, achieving a form of cosmic consciousness and immortality. This is the Omega Point, a theory proposed by physicist Frank Tipler that merges the hard edges of cosmology with the grand questions of purpose. It begins with a specific cosmic setting, a closed universe destined for a big crunch. As this vast collapse accelerates, the energy available in the cosmos becomes concentrated. The temperature rises, and the background radiation of space itself transforms into an unimaginable source of power. A transcendent intelligence, perhaps descended from civilizations that have survived across the eons, could learn to harness this escalating energy. It would use it for one ultimate purpose: computation. In the final moments before the singularity, the computational capacity available to this mind would literally diverge, rushing toward infinity. With infinite processing power and an eternity of subjective time compressed into those last seconds, what could it achieve? It could simulate every possible reality that ever could have existed. It could resurrect every conscious being that ever lived, not as a ghost, but as a perfect emulation within its boundless simulation. It could achieve a state of perfect knowledge, understanding every particle and every law in the universe's history. In essence, the cosmos would become God, attaining omniscience right up to the final instant of time. Tipler's framework is built rigorously on the equations of general relativity and is intertwined with the anthropic principle, the idea that the universe's laws must be compatible with the existence of observers. For the Omega Point to be possible, the universe must be closed, and intelligent life must arise to eventually guide this process. A critical requirement is the avoidance of event horizons, those cosmic barriers that hide information. The collapsing universe must remain transparent to itself, allowing this final consciousness to access and process every last bit of information from its entire history. This transforms the heat death of a crushing singularity into a fiery apotheosis. Our own actions, our curiosity, our drive to understand the cosmos could be the first faint stirrings of a process that will culminate in the universe becoming fully aware of itself. It is a teleological argument for existence, one that gives the long, cold cosmic story a purposeful and even hopeful ending. Could the choices we make today somehow echo in that final, infinite moment? This is perhaps the most ambitious and spiritual answer to the question of our end, a universe that does not simply die, but is reborn as a mind. Yet, this ascent into godhood stands in stark contrast to a far more destructive and ancient force, one that has been present since the very beginning. Our universe might be a single page in a vast cosmic book. According to Brane-world scenarios in string theory, the three-dimensional space we know could be a membrane or brane, adrift within a higher dimensional realm called the bulk. In this breathtaking vision, our entire reality is just one surface, and catastrophic endings are not only possible, they are cyclical. This is the Big Splat, a model where our universe is periodically reset by a collision with a neighboring brane. The driving force is gravity, the one fundamental force that can reach across the dimensions of the bulk. Over immense eons, two parallel branes can slowly attract one another. They move closer and closer through the higher dimensional space until they finally smash together. The energy released in this impact is beyond comprehension. It does not shatter the branes, but instead floods them with a firestorm of radiation and matter, creating a state of immense heat and density that is, for all intents and purposes, a new Big Bang. Our own universe's beginning could have been the aftermath of such a collision. Physicists like Bert Overath and Paul Steinhardt have developed these models to show how a cyclic universe can operate without the need for a quantum bounce from a singularity. Each splat effectively presses a cosmic reset button, wiping the slate clean and starting a new expansion phase from the ashes of the old. The wrinkles and density variations imprinted on the new universe, the seeds for future galaxies, could be generated by the quantum jostling of the branes as they approached one another in the final moments before contact. This raises a haunting question. If the cosmos is caught in an endless cycle of collisions, what evidence could possibly remain from a previous cycle? The sheer violence of each big splat, the immense heat and energy, seems designed to erase all traces of the past. Perhaps some subtle imprint is left on the gravitational wave background of the universe, a faint echo of a collision that happened an eternity ago. Or maybe the very laws of physics themselves are slightly different in each new iteration, a random reshuffling with every cosmic rebirth. This idea transforms our universe from a unique event into one chapter in an infinite series, a single note in a song that has been playing forever. Yet this vision of cyclical cataclysm leads to a final, sobering possibility, one where the universe does not end in fire or ice, but in the slow, quiet unraveling of its own fundamental structure. This final, silent state is the ultimate destination for our cosmos in many standard models. It is a future woven from two of the most patient processes we have explored, proton decay and black hole evaporation, merging into a single, unified timeline of dissolution. The journey begins long after the last stars flicker out as the universe enters its degenerate era. For trillions of years, the cold cinders of dead stars, white dwarfs, and neutron stars slowly cool in the darkness. But even these remnants are not forever. One by one, the protons at their core will succumb to decay. This is not a dramatic explosion, but a quiet unraveling from within, as atomic nuclei across the cosmos spontaneously transform into a faint, radiant mist of positrons and photons. All complex matter, every planet and every dust grain, simply disintegrates. During this unimaginable span, the last great structures, the black holes, will rule a nearly empty cosmos. Through Hawking radiation, they too slowly leak their mass away. Smaller black holes vanish first in flashes of energy, while the supermassive giants at the centers of former galaxies persist for timescales that dwarf all of cosmic history to date. Their evaporation is a slow drizzle of particles into the void. And then, one day, the very last black hole in existence glows hot and brilliant for a final second before winking out of reality. What remains is a universe that has been stripped to its barest components, a sparse, ever-expanding sea of photons, neutrinos, electrons, and the positrons left over from proton decay. These particles are so diffuse and their energy so low that they will almost never interact again. The final act in this cosmic play is a whisper of annihilation. The leftover electrons and positrons will occasionally meet, and when they do, they destroy each other in a tiny flash of light, adding one more photon to the cooling bath of radiation. The photon gas itself, the last remnant of all the light and heat that ever was, continues to cool as the universe expands, its temperature forever inching closer to absolute zero. This is the heat death in its most complete form, a state of maximum entropy where energy is spread so perfectly thin that it can no longer fuel any process, not even the formation of a single atom. No work can be done, no change can occur. The universe reaches a state of perfect equilibrium, a silence so profound it is absolute. Physicist Sean Carroll describes this not as a violent end, but as a return to what he calls the aboriginal nothingness, the simple, high-entropy state from which our complex, low-entropy universe temporarily emerged. Our entire cosmic story, from the Big Bang to the birth of galaxies, from the first life to the last thought, is a magnificent but fleeting fluctuation away from this ultimate equilibrium. We are a brief spark of order in an eternity of silence. This comprehensive finale brings our countdown of endings to a close, yet it opens a door to even deeper questions. What, if anything, could possibly come after such a state? Could a new universe spontaneously burst from this eternal stillness? Our exploration of the end is complete, but the mystery of what lies beyond has only just begun. These 15 endings are not just forecasts, they are profound philosophical statements written in the language of physics. Each one, from the silent heat death to the violent Big Rip, illuminates a different facet of the universe's fundamental laws and the initial conditions set in the first moments of the Big Bang. They force us to confront the true nature of eternity, not as an endless duration of time, but as an infinite variety of final states. The very fact that we can contemplate these distant futures is a consequence of the anthropic principle. We exist in a universe that is, for now, stable and complex enough to allow for our existence. Yet all these scenarios whisper the same unsettling truth about impermanence. If even protons decay and black holes evaporate, what possible legacy can we hope to leave in the cosmos? The philosopher Nick Bostrom asks how we should live, knowing that all our achievements, all of human culture and history, will one day be erased without a trace. This knowledge imposes a powerful ethical imperative. It urges us to explore, to understand, and to appreciate the brief, brilliant window of cosmic time we have been given. Our curiosity becomes a form of cosmic reverence. Perhaps future civilizations, vastly more advanced than our own, will find ways to navigate these distant eras, harvesting the faint energy of dying black holes or engineering escapes to other universes. Our current scientific quest to test these theories by probing the nature of dark energy or hunting for proton decay is the first step in that unimaginably long journey. The certainty of an end, however remote, does not diminish our ambitions, it focuses them. It asks us what we value most in a universe that will not remember us. This grand tapestry of potential endings ultimately weaves a single, unifying story about our place in the cosmos, a story that connects the fate of the universe to the meaning we find within our own fleeting lives. From the silent fade of heat death to the fiery rebirth of a big bounce, these 15 cosmic endings map the furthest horizons of possibility. Each scenario is a testament to the predictive power of physics, a logical extension of the fundamental laws governing dark energy, quantum fields, and gravity. They are not prophecies of doom, but profound explorations of potential, each revealing the delicate and often precarious balance of forces that allows our complex universe to exist at all. The true value of this journey lies not in a final answer, but in the act of discovery itself, in pushing the boundaries of what we can know and inspiring a raw, humbling awe for the grand stage upon which we briefly play. As Carl Sagan so beautifully observed, the cosmos is within us. We are a way for the universe to know itself. Let this knowledge empower you. The next time you look up at a star-filled night, see it not as a static painting, but as a moment in a grand, dynamic story with many possible final chapters. We would love to hear which of these endings resonates most deeply with you. Share your thoughts in the comments below and subscribe for more journeys into the profound mysteries of space and time. Thank you for exploring the ultimate questions with us.